increasing or decreasing. It's sort of, at this point, well, it's just a point, so we can't really say it's at a standstill, but obviously the graph at that point can be considered horizontal. So if the graph is horizontal, then the situations could be, it's either a maximum point, a smooth maximum point, or a smooth minimum point, or perhaps something like this, neither maximum nor minimum point. In that case, we call them inflection points, because we can see that the curving of the graph has changed. Here we see it's concave down, the concavity is facing down. Here it's concave up, the concavity is facing up. So we can say that this is an inflection point. This is where the graph actually flexes, changes the curvature. So obviously the points where the derivative of the function equals 0 are extremely important, because they must be special points for the function, special points for the graph. So we call them stationary points because the function is at that moment neither increasing nor decreasing, it's stationary. By the way, if the gradient is positive, then we can say that the function is increasing. If the gradient is negative, then we might say that the function is decreasing at that point, going down, because the tangent line actually reflects the behavior of the function itself. So it's either increasing or decreasing or stationary at that point. And right now we are interested in these stationary points where the tangent line is horizontal, where the gradient is equal to 0. So how can we define a maximum point? When do we say that some point is a maximum point for a function? Disregarding derivatives now. Forget about derivatives. And the tangent lines, so how can you describe a point explaining that it's a maximum point?
The peak of a parabola?
When derivative
The peak of a parabola, if we have a parabola. If we don't have a parabola, but some other curve.
When derivative change side from
Yes, but if we forget derivatives,
okay.
in terms of simple minimum maximum. So it is the top, it's the peak, which means all the other values of the function nearby are less than the function value at this point. So we might say that this point is a maximum point if f at x0 is greater than all the other function values, well, not totally all, but obviously close enough to this. Close enough to this. So if I take some neighborhood around the point x0, some neighborhood, very, very short, it can be very, very small, it doesn't have to be large, it can be a very, very, very short segment. It's enough that it exists. So if there exists a very close, well, some close enough neighborhood around the point x0, such that f at x0 is really the greatest function value in that neighborhood, then we call it a maximum point. And in a similar way, if we can find a neighborhood where all the function values are greater than the function value at this point, then we can call it the minimum point. And we already saw that it is the local minimum. When we investigate functions, we are usually interested in local minimums. It doesn't matter that at this point the function value is less. It doesn't matter that at this point the function value is more than the maximum. Because they are local. You know how functions behave themselves. They can do things like this. So it doesn't mean that these two are not maximum points. They are. These two are minimum points. They are local minimums. That's why I'm talking about this neighborhood. I'm not talking globally. I'm not talking for all the possible values of x. No, only in the closest, nearest neighborhood. So this is the definition of a minimum or maximum point, by which we understand the local minimum the local maximum. Because of course the function will increase and decrease, and it's not necessarily for a function to have one minimum or one maximum point, or to have any. The thing is that locally this is the least value. Locally this is the greatest value. It doesn't matter that somewhere else the function is changing again and the values are exceeding those values again. So what matters is that this is the peak, or this is the bottom of the valley. This is what we are mostly interested in when we investigate functions. And so we can use derivatives to investigate the increase, decrease, minimum, maximum points of a function. So obviously, if in some segment the derivative of a function is positive, it means that at that segment the function is increasing. If the derivative in some segment is negative, it means the function value, the function is decreasing, going down. And if we have a point where the derivative equals 0, it's called a stationary point because the function stands still for a moment. Stationary point, which could be one of three possibilities. It could be local maximum point, it could be local minimum point, or it could be a horizontal inflection. It could be a horizontal inflection point, but we will investigate inflections later when we deal with second order derivatives and functions, graphs that are curved concave up or concave down. So today we are interested in these, but it's important to understand that there is a possibility that the point which is stationary, the derivative is 0, the function itself doesn't have a maximum or a minimum there. It's simply a horizontal inflection point. So yes, it is stationary, it could be maximum or minimum, but not necessarily, because there is this third possibility. Maximum and minimum points are called the extreme points or extremum points, or extrema from Latin. But again, you have to understand that they are local extrema. So local minimum, local maximum. In other areas, in other segments of the domain, the function might reach values greater or less than these. So how do we investigate a function? What can we tell about the graph from the sign of the derivative? Well, obviously we can, if we split the real number axis, the x-axis, into segments where the derivative has the same sign, we can actually decide whether the function is increasing or decreasing in each part, and therefore we can see where exactly this function can reach minimum or maximum points. So let's have a look at the first example. So for instance, the function is x to the fourth minus 4x cubed, and let's investigate this function. So first of all, we have to find the derivative. 4x cubed minus 12x squared. Now we have to solve an equation. Let's see at which points the derivative equals 0. Last week we had actually exercises about the tangent lines. You were asked to find at which point the tangent to the graph has a 45-degree angle with the x-axis, at which point the gradient equals 0, at which point the gradient is this, at which point the gradient is that. So for minimum maximum points, we must require that the gradient equals 0. So we ask, okay, 4x cubed minus 12x squared equals 0, 4x squared x minus 3 equals 0, we factorize. So So from this, we can see that there is one point. If x is 0, then the derivative is 0. And also if x is 3, then the derivative is also 0. Now what next? So these 2 points are, let's say, potential minimum maximum points. I don't know yet. Well, I do know, but I pretend that I don't. So I sketch the x-axis. I mark those 2 values, 0 and 3 of the x-axis. And now what I'm going to do, I will make a sign diagram. I will make a sign diagram for the derivative. In other words, now I'm looking at the derivative. I know that at these 2 points, the derivative is 0. So at these 2 points, the derivative is 0. Now what about the signs in between? So if x is very, very large, the square is positive, and a large number, for example 100 minus 3, is also positive. So I can write that if x is greater than 3, then the derivative is positive. Now if x is positive between 0 and 3, if x is positive but less than 3, so it will be minus, and if x is negative,
Plus.
no, got you.
Plus minus.
Yeah, minus.
It's
Because
still-
the square.
Yes, the square doesn't change the sign.
Yeah.
See how easy it is to catch you. All right, now the function itself. I know that. Minus.
No, we got you.
Sometimes it happens. All right, now, I know that if the function derivative is negative in some segment, in that segment the function is decreasing. All right, I depict it, I show it by an arrow going downwards, but it's not a vertical arrow. Please make this arrow pointing to the right, because we are looking at the behavior of the graph. So the function, as x increases, the function is decreasing. So don't do it vertically. It's always slumped. Now, still decreasing, all right, and now this is increasing. So we can see that obviously, because it first decreases and then increases, this must be the minimum point. This must be the minimum of function. So I can write that the minimum of this function is at point 3, and I have to find the value of the function to put there, not of the derivative. The derivative is 0 at that point. But if I need to know the coordinate in the graph, I need to put it into the original function, not into the derivative, because I already know the derivative. It's 0. So 3 to the 4th is 81, minus 108 is minus 27. So this is the minimum point, and I can actually make a point in my system of coordinates. Now this is obviously an inflection point, because the function decreases, sort of stops for a moment, and then goes on decreasing. It's not a minimum and not a maximum, because the sign of the derivative is the same on both sides. So I can write that this is a horizontal inflection at the point 0, 0. So I have actually, I didn't sketch it, of course, I made my computer do it. You have the graph there, an approximate graph, obviously. The scale is whatever it is. So we can see that the function decreases, then it reaches the inflection point at the point 0, 0. Then it goes on decreasing. At the x value 3, y value minus 27, it reaches the minimum point, and then it starts increasing again. So it looks something like this if it's an inflection point. By the way, there must be, we can see that there must be another inflection point, because I need a smooth curve, so that somewhere there will be another inflection where the graph makes another S shape. So there must be something there, but we are not interested in those right at this moment. At this moment, I'm more interested in this and in this. By the way, at this point, I'm not requiring you to sketch the graph. I'm simply providing the graph as an illustration, so that you understand what this diagram, which is only a diagram, it's not a graph, it's not even an approximate sketch, what this diagram actually means in reality for the actual function. So I'm simply providing an illustration, but I'm not requiring you to do it now. So we can see there are both these possibilities. And another one, a cubic function, 2x cubed plus 3x squared minus 12x plus 5. So the derivative is 6x squared plus 6x minus 12. I can factorize. I take 6 out, x squared plus x minus 2, and I can factorize it further, x plus 2, x minus 1, because this way I can already see the zeros of the derivative. I can already see that the derivative will be equal to 0 if x is minus 2 or if x is 1. Alright, so now x, the derivative of the function, I'm on both points, minus 2, 1. Now I look at the derivative. I'm looking at the derivative in whichever form you like it. You can look at the derivative here where it's factorized, or you can look at the derivative there. It doesn't matter. What matters is the signs you put there. So obviously for large positive values of x, both these factors will be positive. If x is less than 1, but greater than minus 2, for example 0, we can see that this is going to be negative. And if x is very, very negative, for example minus 100, this will be negative, the product will be positive. So now for this function we can see it increases, decreases, increases again. So obviously this is the maximum point, the top, the peak of the mountain, and this is the bottom of the valley, so this will be the minimum point. And of course we need both the coordinates, maximum and minus 2. Okay, I'll cheat, 25. And minimum point at 1, and if this is 1, it's easier, then it's minus 2. Okay, so I can find 2 very special points on that graph. Obviously, there are more special points to be found. We can find the intersections with the axes of the coordinates. We can find the inflection point of this function of this graph. And we need more things to be able to sketch this graph accurately. But for now, it's just an illustration from me or from my computer. The way this function acts, it's this last diagram, the last graph on this paper. Alright, so now we have another problem. Not all the extreme points are stationary. It is possible to have a spiky kind of minimum or maximum, and spiky is not a mathematical term. It's just the way I chose to describe this. For instance, if we have the function as shown, cube root of x squared, First of all, the domain of this function, all the real numbers. For all real numbers, it is possible to find the square, which will be positive, and then find the cube root of that square, which will obviously also be positive, except for when x is 0, but cube root of 0 is 0. So the domain of this function is all the real numbers. The set of all real numbers. Now, if we if we derive this function, the derivative of this function, which is x to the power 2/3 derived, remember the derivative of the power, it is 2/3 times x to the power minus 1/3, subtract 1. So this means it is 2 divided by 3 u roots of x. So this is what the derivative actually looks like. Now for this we see, this derivative is not defined when x is 0. The function is defined for all the values of x, for all the real numbers. The derivative, we can see, we cannot divide by 0, forget the limits. We cannot divide by 0, so the derivative is not defined when x equals 0. So we can ask for the derivative to be equal to 0. No, there's no such x value. Such x values, no, such x. So the derivative is never equal to 0, but there is a point that it doesn't, where it doesn't exist. If x is 0, the derivative of 0 does not exist. Does not exist, because we cannot divide by 0. Well, of course, remembering limits, we can say, okay, but what if we try to divide by 0? What happens then? Then obviously the derivative becomes infinity. So in other words, very close to 0, the derivative becomes very, very, very large. Besides, if x is positive, the derivative is positive, infinity. And if x is negative, the negative 0, the left-hand limit, then the derivative is obviously the negative infinity. But we can say that it doesn't exist because we do not divide by 0. So in this case, if we had some points where the derivative equals 0, we would mark those points on the x-axis, on the number line. Because we don't have such points, we don't mark them, we don't have anything to mark. But we also mark those critical points where the denominator becomes equal to 0. In other words, the points where the derivative does not exist. And we also mark the points where the function does not exist. If the function is not continuous at some points, if it has vertical asymptotes, for example, then we have to mark those as well. So we'll gradually get more and more complicated examples. So in this case, if x is 0, the derivative does not exist. But we can see that if x is positive, then the derivative is positive. If negative, then negative. So the function itself, I can see that it's decreasing, and for positive numbers, it's increasing, and it exists at 0. Where x is 0, it does exist. So if the function is defined, the function has a point there, it must be the minimum point, because before that point the function has been decreasing, after this point the function has been increasing. So it is a minimum, but it's a strange kind of minimum. It's not the horizontal minimum. It's the tangent line is not horizontal because the gradient seems to be infinity. So this means that this is still a minimum point, 0, 0 from there. If x is 0, the function value is 0. And the graph is actually shown in the diagram. That's the screen down from my graphing calculator. So what happens is the function behaves like this, which means you can imagine the tangent line is vertical. We can imagine that the tangent line is vertical here. So this is what the infinity, derivative infinity, actually means. The tangent line must be vertical at that point. The x equals 0 is allowed for the function. For the derivative, it means, it looks like the derivative is infinity. So the straight line with the gradient infinity is vertical. So in this case, it is possible to have a minimum or a maximum point, simply because the signs change, the signs of the derivative change on both sides going through the 0, and the derivative itself does not exist, at least not a finite derivative. It's infinity, it's not a finite one. So a vertical line is the tangent line for this. And the graph looks like this. And this, yes, it's a real function. It exists. Yes?
Yeah, but what if the function doesn't change its direction?
if the derivative doesn't change its sign, then we might have a vertical inflection. It might be, let's say, the derivative is negative, the tangent is vertical, and the derivative is still negative. It might look like this. So then it's a vertical inflection. It's possible.
But this won't be a minimum or maximum.
This is not. This is nothing. This is an inflection point. That one, the previously, in the first example, this one was the horizontal inflection point. The function flexes at this point, but the tangent is horizontal. In this case, it's a vertical inflection point. The function again flexes over, but the tangent line is vertical. It's not a minimum or maximum. We can see it's not the least nor the greatest value in any neighborhood here.
And it's not a stationary point.
No. It's not stationary point because the tangent is not horizontal. Stationary means stand still. Stand still means neither increasing nor decreasing. So that means tangent is horizontal.
So then we can call it flexible point.
Inflection point, yes, but it's
Yeah,
it's not minimum nor maximum. And obviously, now you can imagine what we are going to do tomorrow. We have horizontal inflection point, vertical inflection point. Who's to say that we cannot have a slant inflection point like this, where the tangent is actually neither vertical nor horizontal, but a slant line, just like this. So we can have this kind of inflection as well, but this is not a minimum nor maximum. Minimum and maximum only happens where the derivative changes sign. Decreases first, increases afterwards, that's a minimum point, or first increases and then decreases, that would be a maximum point. The sign of the change of sign of the derivative is the indicator of minimum maximum point. Unless, of course, the function has a discontinuity at that point. All right, now there's another thing. So regarding the global minimum and global maximum points, something that was already pointed out. For example, I might have a function something like this. For instance, and the axes are this, and I am interested in the absolutely greatest and absolutely least value of this function on some segment. Obviously, I cannot have all the domain, the whole real number set, because there might be no least value or no greatest value. But I could talk about some segment, and I might say, all right, I have this segment, x is between a and b. X is between a and b, and I need to find the absolutely greatest and the absolutely least value of this function on that segment. For some reasons, it might be some methods of optimization, or perhaps it could be some linear programming or something. I simply need to find the greatest or the least value for this function. So in this case, for example, if I find the minimum point, the local minimum point, compared to this point, yes, it is the least, because this function, you can see, the function doesn't go any lower. So on this segment, from A to B, on this segment only, the least value is indeed at the minimum point. In this particular example, there might be other examples. So if I want to see the maximum point, okay, I find the local maximum. Can I say this is the greatest value of this function? No. In this segment from A to B, I can find this value. This is the greatest value. So there is a difference. These are the local minimum maximum points, but sometimes we are indeed interested interested in the absolute minimum, the global minimum maximum points. In other words, global, what's the world? Global means worldwide. Where's the world? The world is from A to B. This is our world. This is why we say global. Global in this interval. Global in this, on this segment, like this. So this is the whole world. This is what we mean by global. And we can see that the potential greatest or least values of this function on some segment, it has to be closed segment, obviously. Both points have to be closed, not open points. It could be in one of the extreme points, in the maximum point or in the minimum point, but it could also be at the ends of that segment. It's also possible that at the ends of that segment, the functional value is greater or less than our local maximum, local minimum. We can't know until we check. And to solve this kind of problem, if you are told to find the greatest value of the function on some segment, the least value of some function on this segment, we don't actually calculate, we don't actually investigate the signs of the derivative. I don't care whether this is a minimum or maximum point. What I do is I find the critical points, x1, x2, and I find all the function values, the function value at x1, the function value at x2, and also at the ends of the segment, the function value at A, the function value at B. This is where possibly the greatest and the least values can be situated, nowhere else. It's either in these stationary points, the critical points, or at the ends of this segment. So to save ourselves a lot of work, we do not investigate the signs of the derivative. We do not investigate increase, decrease of the function. We simply check the values at these 4 points, or more, or less. Depends on how many points we have there. So there is a difference from the previous tasks. In the previous tasks, we are investigating the local minimums, local maximum points, so the local extrema. In this case, we are simply interested in the possibly greatest, the greatest possible function value in this segment, the least possible function value in this segment. So I don't care whether this is a minimum or maximum point. I only care about the values of the function. And so I simply check these values and I pick, oh, this is the greatest one, this is the least one, and I'm happy. Yes?
Yeah, about the A and B
Yes.
functions. Why we need to find the A and B functions for this?
Because you see, if I find the function value at the maximum point and say, oh, this is the greatest possible value in this segment, look at what happens. It might be not this case. It could be less than that maximum point, but it could be higher up than the local maximum point. And therefore we need to check the ends, because we don't want the function to just go out of control. Don't want to have a runaway function. So yes, we might have a local minimum, local maximum. Like I'm at the top of the hill and I say, oh yes, I'm on the top of the world, and then I look, oh no, there's another one.
So we should check who the segment of this.
Yes. We should check the critical points, meaning the points where the derivative equals 0, or perhaps does not exist, but that's very, very rare, and the ends of the segment. By the way, if the function has more than 1 or 2 critical points, stationary points, we only check those which are inside the segment. If I have another critical point, for example, if I have another minimum point, for instance, outside, I don't care about this one because I'm only interested in the segment from A to B. So even if I have an x3, it is outside that segment, so I ignore it. I find it, I understand that yes, there is another one, but I don't have to check it because my interest is only within this segment. So we may leave the points outside the segment outside. Yes, more questions?
You said that you don't care about the signs, but in order to find x1 and x2, you should...
We find the values. We don't care about the signs of derivatives. We don't have to check plus, minus, plus, increasing, decreasing, increasing, because it's not so important. That's extra work. We are lazy. Aren't you? You are. We are all lazy. Why should we do extra work if it's enough to simply check the values of these 4 points and choose which one is which? It might be the stationary points. It might be the end points.
What about the surface?
Surface.
Yes, that's it.
You mean the two variable functions?
Yeah.
Well, basically the same. We find the potential extreme points where the first derivatives are both 0. But if we are interested in some domain, in some area of this function, we need also to check the borderline, the boundary of that, which is obviously difficult. This is messy because there are infinitely many values to check. So we have to decide something. We have to decide about something. Have to probably look up some more complicated methods, usually.
Integrals.
Derivatives, partial derivatives. For that we need partial derivatives. Integrals are necessary for other purposes. So the fourth example, supposing the function we have is x plus 1 squared times x minus 2 plus 2 on the segment from 0 to 2. We find the derivative. Which is product rule. And for product rule, we have more or less a chain rule. So x plus 1 squared derived is 2 times x plus 1 times 1 times x minus 2 plus x plus 1 squared not derived times 1 times this one derived. And 2 derivative is 0. So to make things easier, I can factorize this. I can take x plus 1 outside. And inside 2 times this is 2x minus 4 plus again x plus 1, which is x plus 1 times 3x minus 3. All right. So this is the derivative. Yes, I can take 3 out. It's not strictly necessary, because from this I see this is 0 if x is minus 1 or if x is plus 1. If I can see the root, there's no need to do anything more. I look at this and I already see the root. Or we can take 3 out of that second factor. So now, all right, minus 1, 1, but we are interested only in the segment from 0 to 2. So 0, 2, and I will be interested only in this segment. So I will ignore this point, even though I found that it is a stationary point. I ignore it because I'm only interested in x values from 0 to 2. So I don't have to check anything there, but for these I will do f of 0, f of 1, f of 2, and from there I will see which one is the greatest and which one is the least. So if x is 0, 1 times minus 2 is minus 2 plus 2 is 0 again. If x is 2, by the way, then this is 0 and the function value is 2. And if x is 1, then we have 2 squared, it's 4 times minus 1 is minus 4. Minus 4 plus 2 is minus 2. I simply put these values, the endpoints and the critical point that's inside the segment, into the original function and check the values. So I can say this is the greatest. Oh, sorry, this is the least. This is the greatest. This is the greatest and this is the least. And that's it.
So if we require to find is this graph is increasing or decreasing in this segment?
Then that would be something different. If we need to find the increase and decrease, then we need to look at the signs of the derivative, positive derivative, negative derivative. But if our only purpose is to find the greatest possible value in this segment, then why bother? We just check these critical points. These are the points where it might be possible, no other points. So I simply check those points. So it depends on what the purpose is. If the purpose is to investigate the shape of the function, then we look at those arrows and plus and minus and everything, the sign diagram. If our purpose is find the least possible value, find the greatest possible value, then we do this. Then there's no need for increase and decrease for that kind of investigation. Okay, now let's have a look at those exercises. Let's have a look at those exercises. First of all, let's look at number 2. Let's look at number 2. The graph of the derivative is given. The graph of the derivative is given. The graph that you see there is not the graph of the function, but the graph of the derivative. So how can we find the intervals of monotonicity of the function? Monotonicity means increase and decrease. We say that the function is monotonous if it's just only increasing or only decreasing. So monotonous means going in the same direction all the time. Only increasing or only decreasing.
Can we get an original function?
No. 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 We only have the graph of the derivative. We only have the graph of the derivative. To find the original function, we would need to integrate.
Yeah.
To integrate, we would need a formula. We don't have a formula to integrate.
We can find the formula.
No. No, we have this f derivative. So let's see. From -5 to -4, the function, the derivative is positive. So the original function would be increasing. Now, between x is -4 and x is -2, the derivative is negative, which means the original function, we have no idea what it looks like, but we know that it's decreasing.
So the first part is also written, yeah?
Asymptote and something like this. All right, this is what you have. So I can say that from -5 to -4, the original, so the derivative is positive, which means the original function is increasing between x values, -5 or and -4. Now between -4 and -2, the derivative is negative, which means the original function would be decreasing in this part, but I don't know exactly how. Now, from -2 to 0, again, the derivative is positive, which means the original function would be increasing. Between 0 and 1, the derivative is negative, which means the original function is decreasing. And if the x is greater than 1, then the derivative is positive, which means the function is increasing again. By the way, from this, we can't really tell whether this will be a vertical asymptote for the function as well, or it might be the spiky type of minimum. We don't know. We have no way of telling at this point. We have no way of knowing. But The sign of the derivative determines the behavior of the function. The sign is negative, the function is decreasing. The derivative is positive, the function is increasing. The derivative is negative, the function is decreasing. The derivative is positive, the function is increasing. But we don't know the actual shape of this function. Yes?
And what about the name inflection?
Inflection?
Yeah, inflection.
We don't know, or we might say the inflection points are actually where the derivative has maximum or minimum points. These are possible inflection points because the second derivative will be 0 there. But we'll talk about that some more tomorrow, about inflections. But yes, this graph actually tells us that there are inflections. Actually, not just possible, but because we see that the derivative is increasing then decreasing, then the second derivative would be positive then negative, so that there would be an inflection point. All right. So now we have exercise 1, where we have to determine the extreme points of the function and state their nature and decide the intervals of monotonicity, or, well, we don't exactly have to write the intervals of monotonicity, we can simply indicate them by arrows. We can simply indicate them using arrows. And in exercise 3, find the greatest and least values. So, we don't have time for 11 functions, but obviously we can do at least some. Yes? This one? Let me see. 3a. So 24x squared minus 12x cubed. Oh, I lost the cube. I lost the cube, sorry. Yes. Okay, yes. There's an error in, yes, that's yours. There is an error in the answers for 3a. I seem to have lost, yes, I lost something, I think, or maybe, yes. I will correct it in the file. I just have to remind myself. Yes? This is the graph of the output. Something like this would be the graph of the original function. We don't know how high, how much stretched up or down, what way